that you understand it, is you can take these rules, and we're just gonna do some practices, okay? So in the first one, first off, you tell me how many significant figures in 0.120? 3, right? Remember zeros are always, I know the 1 and the 2 are significant. Zeros out front are never significant. Zeros at the end are only significant if there's a decimal, right? So since there's a decimal, those are your 3 significant figures. What about 2.782? All of them, right? So any non-zero numbers are always significant. So now, do the math. Take 0.120, multiply it by 2.782. Like I said, if you need a calculator. So this is 0.33384. Everybody got that? Okay, how many significant figures in that number? 5, right? The 0 out front is not. So there's 5. I can't have 5. That is a more exact number than either of the numbers in my problem. So the rule says you're going to round to the least number of significant figures in the problem. So how many do I have to round to? 3, okay? So you start from the left, underline the first 3 significant figures you get to in your answer, and then figure out how you round with the next number. So remember that 0 is not significant. I'm going to keep it, but it's not a significant figure. So those 0.333, those 3s are my significant figures. The next number is an 8, so what's that going to do? It'll round it up. 3, 3, 4. Okay, so everybody sees there's 3 significant figures in your answer. So it's not just like random how you round things. It really is based on the number of significant figures in the problem. So what about the next one? 12,500 has 3, because there's no decimal place. So those zeros at the end are not significant. 3.7 is 2. So if I take 12,500 and divide it by 3.7, I get this number with an awful lot of digits, 3,378.378378. I can't keep all of those. That's 10 significant figures. So I got to round to what? 2. So here's the first 2 significant figures. The next number's a 7. What will that do? So the 7 is going to round the 3 to a 4. What else do I have to add? The 0, 0. So see how that's 3,378? I'm going to round it to 3,400. It's probably been stepped on. Things just happen. They like lead our tough life. Okay? But now, so notice in this, I did have to add those 2 zeros at the end. I don't put a decimal place. The zeros are showing the size of the number. So you might have to have zeros out front with the decimal if it's less than 1. You might have to have zeros at the end if it's a big number. You have to show the size of the number. But remember, those are not considered significant figures. Now, what do I do with this one? So first, 456.025, how many significant figures? 6, all of them. 2.30. 3. 19.2544, 6. Okay, just practicing significant figures. Everybody sees those. But addition and subtraction, you don't care about significant figures. Addition and subtraction, first do the math. 256.025 plus 2.3 plus 19.2544. And I got 477.5794. Okay, so how do I know how to round? I can't keep all of those. I'm going to round to what decimal place? Okay, so here I have 3, here I have 2, here I have 4. So I'm going to round to 2, the smallest number in common. Okay? So you just look at each one, and in fact, if there's no decimal, you would just round to 1, or you would just round to the ones place. But this one, since it's got 3, I'm going to keep 3 decimal, 2 decimal, 4 decimal, I've got to keep 2. So the 5, 7. So the next number is a 9. So what's that going to do? So that's going to be 5, 8. So it'd be 477.58. Okay, so try the next one. 25.896 minus 15.7896. Like I said, do the math first. Always do the math first. And then worry about the rounding. So I got 10.1064. I'm going to round this to what? No, so see I have 3 decimal places and 4 decimal places, so that means that I'm going to round to 3. The number of decimal places in common, so the number I've got to round is a 4, so what happens? It just rounds off. So I'd end up with 10.106. So if you do addition and subtraction, compare the decimal place numbers. The smallest number of decimal places tells you how to do the rounding. Let's try this next one. So you can see again, you end up with a big long string of numbers, but you can't keep all of those. So smallest number of significant figures. So how many significant figures in this number? 5. So 5, remember zeros out front, don't count. Even though those zeros, I know you're thinking like, well, those zeros are past the decimal, but they're out front. There's no non-zero number in front of them. So zeros out front are never significant. So just remember, those are never going to end up being significant figures. Zeros at the end are significant no matter where the decimal place is. They just have to be at the end of the number. So this one has 5. So the 45100. What about the other one? 0.0256. 3. So this one has 3. So then when I go and look at my number, I've got to round it to 3. So when identifying the first 3 significant figures from the left, I got to keep the 0 point, but it's not significant. So the 1, the 7, and the 6. Those are the ones that I'm going to keep. The next number is a 1, so what happens? Just rounds off, right? So anything that's 5 or up, it rounds the last number up. If it's less than 5, then you just drop it off. But notice that I keep 176. I keep the decimal place to show the size of the number. So the 0 decimal place, that 0 out front is not significant, but you need it to show you how small the number is. So what about this one? So if I have a million with the decimal place, that's an exact number, 1 million times 12.56. Right? So a million times 12.56 ends up being 12,560,000. I can't keep all of those, or can I? How many in the first? How many significant figures in this 1 million decimal place? 7. That's all of them because the decimal place is at the end. So that means all those zeros are measured numbers. 12.56 has 4. So I got to round my answer to 4. So what do I need to do? It's okay as it is, right? Because those zeros at the end, there's no decimal place there. The zeros at the end, the 1, 2, 5, and 6, these are my 4 significant figures. I keep the zeros at the end just to show the size. So big thing, when you multiply and divide, make sure you round your smallest number of, round to the smallest number of significant figures in the problem. That's with multiplication and division. If you're doing addition and subtraction, then you round to the smallest decimal place. Always do the math first, then do the rounding. So in this one, like 9,500.12 plus 3.6 plus 152.1. So I got 9655.82. That's just doing the math. But what would I round that to? It should actually be 820. You round that. $9,656. Agree? Need a decimal, right? So how many in the first one? So I have how many decimal places in the first? 3. How many in the second? How many in the third? So that means that I got to keep that 0.8. So the next number is a 2, so what happens? So that's just going to drop off. So it'll be 9655.8. So see, since there's one decimal place in common with all of them, I'm going to round my answer to the same number of decimal places. Okay, so those are sort of different from each other, multiplication and division compared to addition and subtraction. So you just want to make sure that you practice those. So the other challenge, the last kind of like math part of it, it talks about exponents. And the fact that when you're talking about really big numbers or really small numbers, then it's easier to try and manage them by adding this exponent or scientific notation into account. So definition of scientific notation. Scientific notation is when you take and put a number, make it between 1 and 9. You're going to move your decimal place so your number always becomes between 1 and 9, and you keep any significant figures. Okay, so if I have this, right, so it's 71 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 11 zeros after the 71. So I can't actually put that in my calculator because the calculator will only hold 10 digits, okay? So a way to shorten this is put it in scientific notation. So if you don't see a decimal place, where is it? Like in that number, I don't see a decimal place. It's behind the last zero. So it means that it's, you know that it is at the end. If you don't see a decimal place, it's always at the end. So now I'm going to have to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to have to move my decimal place to the left 12 places, making my number between 1 and 9. So I have to keep the significant figures, right? The 7 and the 1 are significant figures. And I moved this 12 places. So the exponent tells you how far the decimal moved to make that number between 1 and 9. If the exponent is positive, then you know that your number is greater than 1. So you know that your number is bigger than 1. So if I had 1.23 times 10 to the fourth, you tell me what is that number? How would you write it out in normal form? Okay, so see where it has the 4. So the 4, if I want to put it into normal form, that means I'm going to move my decimal place 4 places to the right. So this would make it, add 2 zeros at the end. So I'd have to start here and go 1, 2, 3, 4. So 2, 2, 3 with 2 zeros. So that's if it's a whole number. If the exponent is a positive exponent, you know the number is going to be bigger than 1. If you're going from the number to the exponent, the decimal place always goes to the left. But if you're going from the exponent back to the regular number, then you're going to move your decimal place to the right. But just kind of in your head, always make sure, well, I know my number's got to be bigger than 1. That'll help you remember which way your decimal goes. If it's a negative exponent, though, okay, so if I have this, okay, which comes to, this is like when you start talking about the size of atoms. They're extremely small, okay? So again, you go try to put this in your calculator. It's really difficult to put in your calculator because you really can't put more than 10 digits in the old type of calculators. So the easier way is to put this in an exponent. So you see that the decimal place is behind the very first 0. So you have to go and count. You want to make your number again between 1 and 9. So I've got to move my decimal place and just count as you go. So it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this would be 2.31 times 10 to the negative 13. So a negative exponent tells you that your number is less than 1. And the number for the exponent is how many places you have to move your decimal to make your number between 1 and 10, or 1 and 9, sorry. And notice I kept the 2, 3, and 1 because those are the significant figures in the problem. So what if I have this? What if I had 6.22 times 10 to the minus 5? Write that out in normal form. In which direction? To the left, okay? So what I was trying to do was oh, it just came back. I was trying to get it to change color. Okay, so I'd have to start here, right after the 6. It's a negative 5, so I go 1, 2, 3, 4, 5. So my decimal's here, so that means that I'm going to have 4 zeros in front of my 6. So a negative exponent, make sure that you make your number so it ends up being less than, so 0.000622 would be that answer. Okay, so a couple to practice. Put the first group of them, put them in scientific notation, and the last 3, just write them out in their standard form. Two, 3, 4. All right, see with these ones. So one note that I put down at the bottom is make sure that you remember, okay, which ones are significant figures. So if you have zeros at the end of a number and there's a decimal place, they're a significant figure, so you really do have to keep them. So with the first one, I don't have any decimal places, so I know those zeros at the end, they don't have to stay. They'll get dropped off when you go into exponents. So the decimal places at the end, so it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1.20568 times 10 to the 9th. Okay, everybody got that one? 12,500 decimal places on the end because I don't see it. Those zeros, there's no decimal place in the number, so it's 1, 2, 3, 4. So 1.25 times 10 to the 4th. Sometimes putting things in exponents doesn't really make it all that great, like this one, decimal places here. I move it 2 places over, but I have to keep all those other numbers. So in that one, it would be 2.56000025 times 10 to the 3rd. So it would still end up being like, because all those numbers in the middle, those are all significant figures, so I wouldn't round that. Oh yeah, it's to the second, sorry. To the second. Now what about this one? Which way does my decimal place go? To the right or left? The goal is just make your number between 1 and 9. So it's going to go to, so it's here. So my decimal place is here. So it has to go 1, 2, 3. So 2.5896 times 10 to the -3. So it's a number less than 1. Same thing with the next one. How many places does it move? So you see where it is. You're just making your number between 1 and 9. So you're going to move it 6 places, 4.51. Now I've got to keep those 2 zeros. They're at the end of a number with a decimal. So I would need to keep those in my number. But the zeros out front get dropped off. It's really helpful when you have numbers like this, but it's like, makes your eyes go crazy when you try to read them. So this is 1 times 10 to the 14th. Okay, and I wouldn't put 1.0. You don't have to have a decimal after that. Since it's just 1 is the only significant figure in that number, I would just keep the 1. So I wouldn't have to put 1.0 because that would make 2 significant figures. There's only 1 significant figure in that really big number. Now if I'm going the other direction, if it's 10 to the 6th, which way is my decimal place going to go? To the right. So this is going to be 95123. It'll go 1, 2, 3, 4, 5, 6.
For the problem, the 1 times 10 to the 14th, if I did put 1.0, would it make it wrong?
Yeah, because that would actually give you 2 significant figures, right? So 1.0, that 0 would be a significant figure then. And in this, if it's 100 billion, whatever it is, then that's just a 1. So it's still just the 1 is the only significant figure in the number. So you're only going to keep zeros at the end if there's a decimal place showing that it is. What about the next one? How far does that one go? 1.123 times 10 to the 12th. Decimal place goes to the right. How many zeros? So we end up with 1, 2, 3, 1, 2, 3, 1, 2, 3. So decimal place goes 3, and then 9 more to make the total of 12. But then with this last one, so 9.52, 1, 2, 3 times 10 to the -6, so decimal place here goes to the left. And so in this, 952, 1, 2, 3, so it'll end up with 1, 2, 1, 2, 3, 4, 5, 6, decimal place 0. So I had 5 zeros in front of the 9, then the decimal place. Okay, just make sure that you like remind yourself about this, is you want to make sure that you keep any significant figures, whether you're going from exponents to the full number or from the full number to the exponent. You don't round any significant figures off. So two applications of this, one is percent, the other one is density. So percent is used as a way of showing you how you would round, because most people know what percent is. Most people know, like, if they get an 80% on a test, that means they got 80 out of 100 questions right. So percent, by definition, it's how much you got divided by the total, or the whole amount, and you multiply that answer times 100. So this would be, if I got an 80%, I got 80 points out of 100 possible. So you know, if you took 80 divided by 100, it would be 0.8. So instead of leaving it in a decimal place, you take whatever it is, multiply the answer times 100, and that's your percent. So that's how you end up with an 80%. So pretty much on my exams, I figure it out, and I have like 100-point exams. So on my exams, on my tests, I have questions, and the questions are worth a certain amount, so the total number of points is 100. But I used to teach with a guy, and he used to write tests based on how much material he had covered. So sometimes students would have a 300-point test, sometimes they would have a 400-point test, sometimes there'd be a 600-point test. It depended on how much material he covered. He always said he wrote questions till he got tired. Okay? So sometimes, yeah, so they ended up having like different amounts. So that means, like, okay, if you had a 400-point test, and say that you got 325 points right out of 400, and then you took another test and you got, say, 425 out of a 600-point test, how do you know what your percentage? So that's when students are like, well, I want to know what my percent. So you take what you got, what the part, right, the not full credit, but what you scored, divided by what you could have scored, or the whole, and multiply the answer times 100. So in this first one, it'd be 325 divided by 400 times 100, and I got 81.25%. Whereas if I looked at the 425 divided by 600, that one, I end up with 70.833%. So even though I got like more points, it was a bigger test, so it ended up being a lower score. So that's really what all percent is you're basically just figuring out the fraction and multiplying it times 100, because it makes it easier to put it on a 0 to 100 scale. So you can kind of compare it to how you did before or how you did to other tests. So example in this, just figuring out percentage. If you have 48 coins, 12 are quarters, 20 are nickels, 10 are dimes, the rest are pennies. What is the percent of each coin? So how do I figure out how many are quarters? What is the percentage of quarters? Divided by 48. All right, so you just take 12, the total number of that portion, divided by the total number, times 100. And that comes out being like 25%. So 20 are nickels. So you do the exact same thing. 20 divided by 48 times 100 comes out as about 42%. The dimes, 10 divided by 48 times 100 comes out at about 21%. So those are the quarters, the nickels, and the dimes. So in this, 12, two significant figures, 48, two significant figures, I'd round my number, put it at 25. So same, like 20, that's a pretty, you can't have like a half of a nickel or like more than or less. So exactly 20, exactly 10 dimes. So they would be like exactly, so you'd have a decimal place. So 2 significant figures in those percentages as well. How would you figure out the pennies? What would you do? Okay. Okay, so I could take 48 minus 12 minus 20 minus 10, and that would tell you how many pennies you would have, and then you would divide that by 48, okay? So you could do it that way. Did anybody, would you do it any other way? What would you do?
Add all the percentages together and subtract the 100.
Yeah, because remember, if it's a percent, the total is 100. So you could do that as well. So you could take 100 minus 25 minus 42 minus 21. So either way, it will work out fine. So you could figure out the total amount because you know all the numbers of quarters, dimes, nickels, and pennies. All right, so down here, so 2 infants are in perinatal ICU, so PICU. 1 infant's weight increases from 126 to 147 ounces. The other infant's weight increases from 86 ounces to 103 ounces. So then the last question says, okay, well, which infant had the greatest percent weight increase? So if you were looking for a percent weight increase, what would you do? I want to know a percent weight increase. Okay, so that's initial. This is initial weight, and this is final weight. But I want to know a percent weight increase. So how do I figure out what the increase in weight is? I wouldn't divide those two. If I'm looking for an increase, how would I find that? Yeah, so I would subtract their weight, find the difference in their weight. So 147 minus 126, so that's what, 21 ounces? So that tells you how much weight the baby's gained. What about baby 2? So 103 minus 86. That's 17 ounces. So see, when you just look at these, doesn't it look like baby 1 gained more weight? Well, baby 1 gained more weight. But if I was wondering about a percent, so I want to compare that 21 ounces to how much baby 1 weighed to begin with. So how much did baby 1 weigh to begin with? 126. Take that, the change in the weight compared to how they weighed initially, multiply this answer times 100. What do I do for baby 2 to figure out their percent weight increase? Divided by what? Which is 86. Multiply that times 100. So this is like 16.7%. I'd round that to 17. This one is 17 divided by 86 times 100. So even though baby 2 gained less weight compared to their original size, they've actually had a bigger weight change. And so that's why it's hard to just compare them by just subtracting their weights. Because if I just subtract their weights, I would say baby 1 actually gained more weight. But compared to how big baby 1 was, baby 1 only gained about 16.7% weight. Baby 2 actually gained more. So being able to put them so you can compare, so it's sometimes hard to like compare things side by side equally. Percent lets you do that. So percent, putting things on a scale of 0 to 100, is going to let you do more evaluation about change compared to just looking at flat numbers. Okay, and in these ones, remember, in doing the subtraction, notice I don't have any decimal places, so I just leave my numbers as a whole number by subtracting 147 minus 126. I would just leave the number by subtraction. I don't have to round it or anything with significant figures because adding and subtracting, you go by decimal places. But when I take 21 divided by 126, two significant figures in 21, 126 has 3, so I really should round this to 17. If I want two significant figures in my answer. The other one over there, 17 ounces divided by 86 ounces, both have two significant figures, so this would end up being 20% with the decimal place. So you always kind of go back to those measured values when you try to figure out that rounding. The second one, the second sort of topic that takes this math, rounding, measurements aspect into play is what's called density. So density is a combination of mass and volume. So we've really talked about mass. We said mass is how much stuff any matter takes up. When we think of mass, we always think of weight, because that is like mass compared to gravity. So gravity of the earth pulls on anything that has matter, and so weight is that kind of mass relative to the pull of gravity on that object. If you were in space, you would still have the same mass, but you would not have the same weight, because you don't have the effect of gravity. But you would still have the same substance that makes you up. So that's really where mass comes into play. And remember, that's the gram. Volume is this three-dimensional measurement. So I always think of volume like thinking of like a cup, thinking of a liter. In lab, oftentimes our measurement is going to be the milliliter, because it's a small measurement compared to the large liter. Remember, like the liter bottle. It's a bit large when trying to do things in lab, but we use typically the milliliter in a smaller volume. In the clinical setting, you might see volumes that are not just listed in milliliter. You might see things listed as cc. Has anybody ever seen that? So syringes come as 3 cc syringes. A cc is a cubic centimeter. So all that means is it is, if it was a solid, it is something that would be 1 centimeter tall, 1 centimeter wide, 1 centimeter deep. And a centimeter is just under half an inch. Okay, so that small mark on the metric ruler, that's a cubic centimeter. So just remember, if you see milliliter and you see cc, they're the same thing. So you might see a syringe that says 3 mils. You might see a syringe that says 3 cc. Don't let that throw you. It's actually the same volume. It's just one was always used for a liquid. One was always used for like a cube, for something that can be measured as a solid. But the connection between these two, you can have like 5 pounds of sugar, or you can have 2 ounces of sugar. You can have different amounts of mass of any kind of pure substance. You can also have different volumes, right? So you could have like a cup of sugar, or you could have a tablespoon of sugar, different volumes there. But when you look at mass divided by volume, when you compare the amount of mass something has compared to its volume, this is where you actually get a consistent number. So that is density. It's how much mass something has compared to the volume that it takes up. So by definition, density is equal to mass, the mass of a substance, and it's typically listed in grams, divided by its volume. And the volume is typically listed in milliliters. I mean, it can be liters if we're talking about gases, but for most liquids. So when they were deciding on this was another thing that like led to the metric system and designating this is 1 gram, designating this is 1 milliliter, is because they said, well, we want to have like a standard value. So water became like the standard density value, because they measured out the weight of water. 1 gram of water takes up the space of 1 milliliter. And so it has a density of exactly 1. So it became like the standard. 1 gram of water has a volume of 1 milliliter. So then they can say, okay, anything that's less dense than water will float, right? Like a piece of wood. So you know anything that floats on water is going to be less dense. But if you took like a penny and drop it in water, it falls to the bottom. And so you know that's more dense. So now you have a way of like comparing. So you know the density of water, so you can compare the density of other things based on where they go when they're added to water. We can take any amount of mass of a pure substance and figure out its volume and come up with a density that's going to be uniform. So here's an example. If we have a liter volume of sugar and it has a density of 1.2 grams per mil, we want to know the mass of the sugar. So in these, whenever you have these math problems, you will have measured values, and you'll always know like all but one part of a formula. So in this one, this is one of the simplest formulas that we've got. So to remember that density, D equals M over V. Density equals mass over volume. So again, sometimes it throws people when it's put in like a sentence form. So the big things to do is you pick out, what are the numbers I know? Okay, so what is 1.00? Okay, so that is is it density, is it mass, or is it volume? Right, so I know volume. So I know volume is 1.00 liters. Okay, what else do I know? I know density. Right, so I know that density is 1.29 grams per mil. Now reading the question, what do I want to find? Mass. So just read through your sentence and like underline the units that the measurements that you're given, identify what they are, and then how you're going to apply it. So I want to find mass. So if I have density equals mass divided by volume, I need to have mass all by itself. So here's where we have to do a little rearranging of the formula, like what you did in algebra. So if D equals M over V, if I want to get M all by itself, what do I have to move? So if I multiply both sides by V, right? So I multiply both sides. Remember in algebra, you can multiply both sides. It won't change it. But what is that going to do to the right side? They're going to cancel. So it's a way of being able to move anything in the denominator. It moves to the other side and ends up in the denominator. So now I know volume times density is going to equal mass. So I rearranged the formula. So now I'm going to plug them in. So I'm going to plug in volume. I'm going to plug in density. But I need to do one more thing, and that is compare the units. Do you see that in the units? What is the units for volume? Liters. What are the units for density? Milliliters. So do you see that those two volumes are not the same? Remember that you've got to make sure your units are the same so that they'll cancel when you do the math. So for me, I would always change the one that's found like that only has one unit. So I would change the volume number. So if I have 1.00 liters, I need to change that to milliliters. That way, when I multiply density times volume, milliliters will cancel. So I've got liters. It's just a single setup. So remember that. You just put what you're given times in a line. The unit you're given goes on the bottom. The unit you want goes on top. Milli gets a what? 1,000. 1,000 goes in front of milli. Base unit gets the 1. And that way liters and liters will cancel. 0. So that is 1,000 milliliters. So now just do the math. So volume, we said 1,000 milliliters times density, which is 1.29 grams per mil. So you see that 1.29 grams per mil would be like 1.29 grams over 1 mil. So grams per mil. So that milliliters in the denominator. which is then going to let these cancel. So milliliters and milliliters will cancel, and it'll leave you with your answer in gram. So I just take 1,000 times 1.29 in grams. Before I finish, you go back to the measured problem. So do you see that 1.00, that's a measured value? How many significant figures in that? 3. Okay, 1.29 for density has 3. So that means my answer has to have 3. So do I need to round this? No, it's okay. The 1, the 2, and the 9, 3 significant figures, the 0 at the end, don't need to add a decimal at the end, just leave it as it is. So check the significant figures, they have 3 in my answer. So that's kind of like the steps to doing these. And we'll do these types of problems throughout the entire semester. And so we'll always kind of follow this same process. Identify what you know, what you're trying to find. Check and see what your formula is. Rearrange if you need it. Always check your units. Doing the math and checking your significant figures. I'll give you one more to do. This is another density problem. Set this one up. So what do you know? So you know mass is 678 milligrams. You know volume, which is 0.17 mLs. And so what I want to find? Density. Okay? So we know D equals M over V. So we don't have to rearrange that formula. It's already set up, so D's all by itself. So the second thing is checking the units. So they want the units in grams per mil. So I want to make sure that I have grams per mil as my final units. And what about, do I have to do any converting? Just the mass, right? So I'm going to have to go from milligrams to grams. So 678 milligrams times in the line. Milligrams on the bottom, grams goes on top. Milli always gets 1,000. Grams gets the 1. So this will be 0.678 grams. So now I've got grams and I got mils, so now I just do the math. So 0.678 grams divided by 0.17 ml. 0.678 divided by 0.17. Oh, and I got 3.988235294 grams per mil. Can I keep all those? No. Okay, so now you got to go back up to the problem. How many significant figures does my answer need? 2. 3 significant figures here. 2 significant figures here. So that 1 and the 7. So then you go from the bottom, 3.9. So there's the first 2 significant figures from the left. The next number is an 8. So what's that going to do? So it would round the 8 rounds the 9 up to a 10, and then the 3 becomes a 4. So my answer should be just 4. 4 is 1 significant figure, so it should be 4.0 grams per mil. 2 significant figures in your answer. Okay, so if you came in a little late on your way out, make sure that you pick up a note card. You can write anything you want for exam 1 on the front of a note card. And I don't care if you use the lined side or the unlined side. Some people use the unlined side and write super, super small. So maybe like you will have to write those steps, like it's the reminder for yourself on what you need to do. Maybe you want to write down like what the metric, like metric conversions, maybe an example. And if you write really small, I have seen ones that was like amazing. I couldn't believe that they actually did it. But my suggestion is first start making a list of stuff you think you want on your note card, and then like on Sunday, make your note card. Once you've got all the information and we've covered everything, All the questions on your test come from in class. Okay, so you're not going to have a question that's like in the chapter, but it's not, we didn't talk about it. You won't see any of those. So it's always going to be that. If they're connected, if they're examples that we've talked about, then you might see something like that. But if it's something that would be completely different, then no. Okay. Like in the pre-lecture stuff, or was that in a dynamic study module? Yeah, in the pre-lecture one, usually there's like a hint or there's some background information like on the left side of the screen that you can use to help like work it out. But again, remember, as long as you get an overall average of 80 at the end of the semester, you're fine. Okay, so if you missed a couple of them, it's not that big of a deal. But if you want, like write down which one it was, because some of it had to do with just putting the numbers, like hitting the right subscript, superscript, like combinations. That sometimes is half the problem, trying to make sure that you put it in right. Not that you don't know how to do it, but it's putting it in. All right, so. Yeah, so you get to use this next week. So it's like your cheat sheet. So it's your note card. You're going to bring it with you to class on Monday to take the exam. Okay? All right, so the last thing to talk about is temperature. And most of the time people, like, they know what temperature is, so you know what degrees Fahrenheit is. I just want to do, like, the comparison of what Fahrenheit versus Celsius, and then just introduce the idea of Kelvin, and then that's the end of this chapter. So temperature, remember, is a measure of, like, the vibrational activity of molecules, how hot or how cold it is. We use Fahrenheit, and I will tell you that Fahrenheit it was developed by using just environmental temperatures. So like when it's 100 degrees outside, that is because that was consistently like the hottest day in Europe. And so they were like, oh, we're going to call that 100. And 0 was the coldest day. So when you're talking about areas like in France and in Germany, yeah, it got that cold. So it would get to 0, and that's how they actually ended up coming up with the scale. So it was much more environmental. These were environmental extremes, the 0 and the 100. Coldest day, 0. Hottest day, 100. But then when they came back into, with metric, the idea with metric is we want to have it all kind of on a consistency. So just like they did density, they said density of water is 1 gram per milliliter. They made Celsius, the Celsius scale, where it is the freezing point and boiling points of water are what their scale is on. So 0 degrees Celsius is the freezing point of water, or melting. 100 degrees Celsius then is the boiling point. So trying to kind of put it like on that, keeping water as kind of being the base or the standard for all the number values. So I like this chart right here because this chart shows you kind of how they're different. I don't expect you to like be able to convert from one to the other. I just wanted to show you these, and these numbers are ones that you should know. So first off, the boiling point of water, 100 degrees Celsius, 212 degrees Fahrenheit. So those numbers you should know. 212 Fahrenheit is the boiling point of water, 100 degrees Celsius. Freezing point of water. Water freezes, the roads start getting icy about 32. So 32 degrees Fahrenheit is the equivalent of 0 degrees Celsius. So you can see these, that's the freezing point of water. Up here, there's the boiling point of water. The other number that you'll see a lot is relative to body temperature. So in Fahrenheit, body temperature is 98.6. And remember, that's like a range, okay? Not everybody is exactly 98.6, but that's kind of like the general temperature that the body is. But in Celsius, that's 37. So this third scale that you see over here, the third scale they needed to use in mathematical calculations, math calculations where they couldn't have a negative temperature number. So they found if they took substances and they dropped them below the freezing point of water, but they tried to do math calculations, having a negative temperature affected all of their calculations. And so they came up with a third measurement scale. It's called Kelvin. So you can see it right here. So you can see Kelvin. Kelvin has the exact same degree scale as Celsius. So 1 degree Celsius is like 1 degree Kelvin. They change the exact same scale. But Kelvin is based on what they call absolute zero. So that is the coldest possible temperature that a substance can have. That's the temperature where it basically stops vibrating altogether, because temperature is the measurement of the vibration of molecules. So if you can chill these molecules down and they actually stop vibrating, that is the coldest possible temperature that substances can have. And that is 273 degrees below Celsius. So that would be all the way down here, minus 273 Celsius is equal to 0 degrees Kelvin. We will use Kelvin when we talk about gas laws, but that's pretty much it. But really, the big ones that I want you should know, Fahrenheit boiling point of water, 212, 100 degrees Celsius. Freezing point of water, 32 degrees Fahrenheit, 0 degrees Celsius. And you should know body temperature. So body temperature, 98.6 in Fahrenheit, 37 in Celsius. Celsius and Kelvin have the same scale, but Fahrenheit does not. Fahrenheit changes different. So our body temperatures are designed to sort of be kept at a relatively constant temperature. 98.6 is considered normal. Some of you might be a little warmer, some might be a little colder. Mine's always about like 98. It doesn't ever get up to 98.6. It's typically below. It does vary, and so they do sometimes talk about a range, like a range that's considered normal. In fact, they don't really count that you have a fever until your body temperature is a degree above. So above 99.6, that's really where they start to say, okay, you have a fever, it's above normal. If it's above normal, they call it hyperthermia. Hyper means high. Okay, like the hyperactive kid is the high active. So remember that the word hyper means high. Thermia, think heat. So hyperthermia is if you get too hot. This can sometimes happen if people get heat stroke, if they're out in the heat and they don't drink enough water, their body temperature can go too high, or they can have a severe fever. So a body temperature above 40 degrees Celsius, which is over 104, that can actually be life-threatening. Because above those temperatures, brain function begins to be affected. So people that have fevers over 104 degrees, they may have convulsions. They may end up having permanent brain damage. So having a fever of 99 to 100, it actually is not a bad thing for you because it stimulates your immune system. But if your fever goes above 104, that can actually end up being life-threatening. So the other one, though, is if it goes below. So if your body temperature drops below, really about 97, then they start talking about hypothermia. So think hypo means low, hyper means high, and we'll use those terms again this semester. Thermia just means heat. So in this, why would a patient or a person end up with this? Why would they end up with hypothermia? Yeah. So they're outside in the weather. Okay. So they were like in a car wreck, ended up in cold water. Okay. So you might have a patient that comes in with a really low temperature. That can also happen if things are kind of shutting down. So if the patient has not had adequate medical care and has some type of imbalance, whether it's an infection or if it's some other disease, oftentimes people like in late stages of dying, you will start to see their body temperature goes down. They have a hard time regulating. The term hypo, though, think low. Anything below 95, the interesting thing is this doesn't cause like permanent brain damage. This just causes everything to slow down. That is why they've been able to pull people out that are like blue. They're not breathing. Their heart's not beating. For all intents and purposes, you would say they're dead. But they say that they're not dead until they're warm and dead. So what they do is you bring them and you warm them slowly and then stimulate the heart. And in fact, you can have enough oxygenation that stays under those cold conditions that you don't end up with any long-term side effects. But that can be typically is because of drastic changes in their environmental temperature that they can't monitor it. Okay? All right, so the only other thing, so you have a couple minutes. In chapter 2, so I know you started looking at chapter 2, you had the pre-lecture and stuff. So chapter 2, it is all about like atoms. And really like the first 2 sections gives you like 99% of what's in there. And then the rest is really all about radiation and those changes. So the first one is if we're talking about matter. So we're talking about pure substances all the way just to the elements. Looking at individual elements, they studied and did research and finally determined, okay, atoms are not the smallest indivisible unit of matter, that the atom is actually made up of what they call subatomic particles. So subatomic particles just means that they're the particles that make up the atom. So if I take and draw an atom, so we'll just say, okay, this is an atom. There's 3 different kinds of particles that are found in this space, but 2 of them are found in a very small area, packed in super tight. So these are the protons and the neutrons. And since they're in this really, really small, compact area, they called that area the nucleus. Kind of like the nucleus of the cell, like the little central part. It takes up very little space. So they're alike in this way. Protons and neutrons, they are in the same place in the atom. Protons and neutrons also have mass. Right? So see how there are similarities? Protons and neutrons are both in the nucleus. Protons and neutrons both have mass. But what makes them different is that protons have a positive charge and neutrons are neutral. So both about the same size, both in the same place. They only differ by charge. The other subatomic particle, electrons. Electrons, comparatively, they actually are in that outside area. So the electrons are out here. And they are tiny. They're like little particles of energy. So they have such a small mass. So look at how small they are. Their mass they have almost no mass. They are in constant motion outside of the nucleus. So they don't just sit in one place. They actually have a path or an orbital that they exist in. So they're constantly moving. They're extremely small. And the other thing that makes them different is that they are negatively charged. So you will sometimes see electrons written as an E with the negative. Oftentimes you see the protons written as a P with the positive, and you'll see the neutron written as an N with a little 0, which means like neutral, not charged, like a not symbol. And in fact, most of the space of an atom is empty. So you got this really, really dense core where the mass is located in the nucleus, where protons and neutrons are, and then you have this pretty much empty space with these little tiny particles of energy flying around. Those are the electrons. But you can actually tell information about an atom, the number of protons, neutrons, and electrons that you have by just looking at the periodic table. So there's the example here. So they started off and they actually said, well, we're going to make carbon like our standard, kind of like they did water was like doing density, and water, boiling point, melting point. They were looking for something that was pretty much the consistent. So they said, all right, we're looking at carbon. So on the periodic table, the number that is above the symbol, this is the atomic number. And this tells you the number of protons. The atomic number identifies the element by number and by number of protons. So carbon atoms all have 6 protons. It always has 6 protons. A carbon atom is neutral. So remember, protons are positively charged. So in order to be neutral, the number of protons has to equal the number of. Well, neutrons are neutral. Protons are positively charged. Electrons are negatively charged. So if carbon has 6 protons, it has to have 6 electrons. Okay? So put in your note, the positive protons have to equal the negative electrons. So you can now look at the periodic table. You know the number of protons and electrons in every single element. So if I gave you like F, you look at fluorine, you'd say fluorine has 9 protons and 9 electrons. If you look at sodium, sodium has 11 protons and 11 electrons. You go look at calcium, calcium has 20 protons and 20 electrons. But you don't have to memorize it. You just have to remember the number above the element tells you the number of protons and by default tells you the number of electrons because a neutral atom has equal protons and electrons.
So that's the same as saying, since it's 6 at the top, it's the same number as electrons.
Same, that tells you the number of protons. It also tells you the number of protons and electrons. Okay? So then we just have to figure out the number of neutrons. So I will leave that. We just have to figure out numbers of neutrons. And then for the 30 elements that you've got, like that you're learning, you've learned the names and the symbols. So all of those ones, you should be able to tell me the name. You should be able to tell me the symbol. And then you should be able to use the periodic table to tell me the number of protons and electrons. We'll talk about how you figure out numbers of neutrons next time. Okay? Because that's like, it's really going to end up making a difference. But you don't have to memorize any of it. You just have to know how to use this. Right? So we'll just practice using the periodic table so that you can figure out, when you see Hg, you should be able to tell me that that's what? Mercury. And then if you look at the periodic table, how many protons does it have? 80. Okay? You don't have to do any calculations or anything. The number above the symbol tells you the number of protons. It also tells you the number of electrons because the positive protons and the negative electrons are balance each other out in an atom. Okay? If you did not pick up a card, make sure that you pick up a note card. We finished all of the chapter 1 stuff. The chapter 2 is really a lot of theory. Like it's just a lot like more information. We're going to talk about determining neutrons. We're going to talk about isotopes. We're going to talk about radiation next time. Some of you, especially people that are in vet tech and in dental hygiene, you end up using a lot of x-ray equipment. And like with vet tech, you have to be in the room. You can't just put a dog down and go, okay, don't move, and walk away. Because the dog's going to like jump up and run away. So you end up actually having to be in the room. And so that understanding, talking about protection, talking about shielding and stuff like that, we'll talk about that next time. Okay?